So now this brings us to the third definition of acids and bases. So this is the Lewis definition. So let's take a look at Lewis bases first and define them. A Lewis base, by definition, is an electron pair donor. Okay, so a Lewis base donates an electron pair. Lewis bases are structurally the same as Bronsted-Lowry bases. Both have an available electron pair. Now, this could be a lone pair of electrons, or it could be an electron pair present in a pi bond. And if you remember, pi bond is present in double bonds and triple bonds. A Bronsted-Lowry base always donates this electron pair to a proton, but a Lewis base donates this electron pair to anything that is considered electron deficient. So if the Lewis base is the electron pair donor, then the Lewis acid is the electron pair acceptor. All right? So any species that is electron deficient and capable of accepting an electron pair is counted as a Lewis acid. So all Bronsted-Lowry acids are also Lewis acids, but the reverse is not necessarily true, right? So a Lewis acid is not necessarily a Bronsted-Lowry acid, because in order for a Bronsted-Lowry acid to be an acid, it has to contain a proton. That's the main definition of the Bronsted-Lowry acid, whereas a Lewis acid, as long as it's considered electron deficient, it's a Lewis acid if it can accept a pair of electrons. Common Lewis acids contain elements in group 3A, so you have aluminum and boron, that can accept an electron pair because they do not have completely filled valence shells. So if you look at boron, boron only contains 3 valence electrons, and it can form stable bonds with only 3 single bonds. Right, so boron BF3, for example, is considered a Lewis acid because of the fact that it's electron deficient. It requires another pair of electrons in order to complete its valence shells. So the difference between a Lewis acid and a Lewis base is that a Lewis acid is an electron pair acceptor. So it starts with an AC, right? A Lewis acid is a Lewis acceptor. And so a Lewis base, in that case, is the electron pair donor. All right? So we have a Lewis base that is an electron pair donor. A Lewis acid is the electron pair acceptor. So here's a few examples of Lewis acids and bases. On the left, we have the Lewis bases, and then on the right, we have the Lewis acids. So let's take a look. So a Lewis acid, again, by definition, is anything that contains lone pairs of electrons or pi bonds. So hydroxide contains lone pairs of electrons. Alcohols, the oxygen, contains lone pairs of electrons, and then double bonded carbons also contain pi bonds. And so any of these pairs of electrons can be donated. And so a Lewis base is an electron pair donor. Lewis acids, on the other hand, are compounds that are electron deficient, so they don't have a lot of electrons, right? They lack the electrons. So when you look at water, for example, when you draw the Lewis structure for this, it looks something like this. So you have oxygen, hydrogen, and the oxygen with the lone pairs of electrons. So when you look at the electron negativity difference here, oxygen is obviously more electronegative, and so it will bear a partial negative charge on the oxygen, whereas the hydrogens, they contain partial positive charge, which means that these hydrogen elements, these hydrogen atoms, are considered electron deficient because of this partial positive charge. So that's basically what makes water a Lewis acid. Same thing for methanol, CH3OH. So this hydrogen right here carries a partial positive charge, whereas the oxygen carries a partial negative charge. All right, and in terms of BF3 and aluminum chloride, the same situation here. You have boron, let me use a different color here, boron, and then 3 single bonds to fluorine. And we know that fluorine is the most electronegative element in the periodic table, and so when you look at the polarity of the bonds, they point towards the more electronegative element. So this leaves boron a partial positive charge, right? It's electron deficient, partial positive, whereas the fluorine atoms, they have partial negative charges. And so that's basically what makes boron electron deficient, and the fact that boron only currently has 6 electrons surrounding boron, and it basically violates the octet rule. But boron, as you know, is one of those elements that don't have to follow the octet rule in order to form stable bonds. Same thing with aluminum, right? Aluminum chloride, for example. So you have aluminum that only has basically carries a partial positive charge as well. So aluminum here, chlorine, 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 and obviously partial positive on the aluminum atom. And so that's basically what makes these elements or these molecules acidic in nature, based on Lewis acid's definition. So let's take a look at a few examples here. We have practice problems number 30 and 31. Which species are considered Lewis bases? All right. So first, the definition of Lewis base is anything that is an electron pair donor. All right. So if they have a lone pair of electrons or presence of a double bond or a triple bond, then they're considered Lewis bases. So with the first molecule here, you see that this nitrogen actually has a lone pair of electrons. So sometimes whenever you're writing the chemical formula, the lone pairs of electrons are omitted, right? But NH3 ammonia actually has a lone pair of electrons, and so this makes this molecule a Lewis base. The second one, on the other hand, is not a Lewis base because it doesn't contain any double bonds or lone pairs of electrons. So you draw the Lewis structure, and it looks something like this. So you have 3 hydrogens here, 2 hydrogens here, and 3 hydrogens here. So as you can see, we only have single bonds, no double bonds or triple bonds anywhere, and you don't see any lone pairs of electrons. And so B is not a Lewis base. So let's just circle A to indicate that it is a Lewis base, but B not a Lewis base. The next one here is a hydride ion. So we know that a hydride ion has a lone pair of electrons, and that's why it bears a negative charge. So a hydride ion has a lone pair of electrons, and so yes, it counts as a Lewis base. And finally, we have acetylene, which contains a triple bond, and so this contains pi bonds, and therefore they can act as a Lewis base. And here's practice problem number 31. Which species are Lewis acids? So the definition of a Lewis acid is that they can accept lone pairs of electrons, right? They're electron pair acceptors. So we have boron. Obviously, boron is electron deficient. So when you draw the Lewis dot structure for this one, you have 3 bromine atoms, and so this one carries a partial positive charge, which makes it a Lewis acid. So this one is a yes. And then the second one here is an alcohol. It's ethanol, and you can see that this oxygen right here contains lone pairs of electrons, and so when you look at the polarity of the bonds, you can see that the bond between hydrogen and oxygen is polar itself, right? And so this will carry a partial positive charge, the hydrogen, and then the oxygen carries the partial negative charge. And so this hydrogen here that's bonded to this oxygen is considered electron deficient and therefore is considered Lewis acid. What about this third one here with the carbocation, right? So a carbocation is basically a cation in which the positive charge is on the carbon, hence carbocation. All right, so when you draw the Lewis structure for this one, you have carbon with 3 methyl groups, 3 CH3 groups, right? So you have 1, 2, 3. CH3, CH3, and then another one here. And then it has a positive charge. So as you can see, this carbon lacks a lone pair of electrons in order to complete its shell, right? And so it's electron deficient. So therefore, it can accept an electron pair. And so this is a Lewis acid as well. So that's a yes. And the last one here is a bromide ion, right? So when you look at the Lewis dot symbol for a bromide ion, it looks something like this. So obviously this bromide ion already has a total of 8 electrons surrounding it. And so it has a complete valence shell. So in other words, it doesn't need any more pairs of electrons. In fact, it should be able to donate electrons. And so this one does not count as a Lewis acid. So what does a Lewis acid-base reaction look like? Well, in a Lewis acid-base reaction, a Lewis base donates an electron pair to a Lewis acid. And this chemical reaction can be observed between BF3 and H2O. So in BF3, you can see that this boron right here is electron deficient, whereas the oxygen contains 2 lone pairs of electrons, which can act as a Lewis base because it can donate an electron pair. So the 2 electrons will be shared with this boron right here, and therefore they will form a bond, as you can see. So now this new bond that's formed creates a new compound. So this oxygen will now bear a partial positive charge, and this boron now bears a partial negative charge, completing boron's octet or valence shell. Same thing with oxygen. Oxygen has a complete shell. So now let's look at 2 new terminologies here, electrophiles and nucleophiles. A Lewis acid is also known as an electrophile. So remember that a Lewis acid is an electron pair acceptor, right? Lewis acids are electron deficient or electron poor. They don't have enough electrons, and so they're considered electrophiles. They love electrons, right? So electrophile is love for electrons. So in that case, Lewis base is considered a nucleophile. They have a love for nucleus, right? So Lewis bases are electron pair donor, so they have enough electrons to donate to a nucleus because nucleus contains protons, and protons and electrons interact with each other electrostatically, right? Positive and negative charge. So a Lewis base is also known as a nucleophile because Lewis bases are electron rich. They have a lot of electrons to give, whereas Lewis acids lack electrons. And that's basically what organic chemistry is. It's reactions between electron-rich species and electron-poor species. Lewis acid and Lewis base. In the example that we looked at earlier, there's BF3, which is considered an electrophile because it's electron deficient, right? Boron is electron deficient in this molecule, BF3. And so it wants electrons to complete its shell. Whereas water, H2O, is the nucleophile. It has extra lone pairs of electrons to share. And so it's considered a nucleophile because it's electron rich. So make sure that you know the distinction between these 2 terms, electrophiles and nucleophiles. So here's a few examples of Lewis acid-based reactions that form one new covalent bond. So here is an example of a Lewis acid because this carbon is considered a carbocation, right? There's a positive charge on this carbon, so that means that this carbon is electron deficient. And that's what makes it an electrophile, right? It needs additional electrons to complete its shell. This bromide ion is considered a Lewis base because of the fact that it contains a lot of lone pairs of electrons. It can share one of its lone pairs of electrons, and that's why it's called a nucleophile. It can share its electrons. And so when this bromide ion shares its lone pair with this electron deficient carbon, it forms a new bond as shown in green. And here's another example, a Lewis acid, aluminum chloride. And the reason why is because this aluminum is also electron deficient and it doesn't have a complete octet. And so this alkyl halide here, or ethyl chloride, is acting as a Lewis base or a nucleophile because it has lone pairs of electrons to share with the electron deficient aluminum. And so when it does, it forms a covalent bond between chlorine and aluminum, as shown here again in green. And then this chlorine will bear a partial positive charge and the aluminum will bear a partial negative charge. And here's practice problem number 32. For each reaction, label the Lewis acid and base. Use curved arrow notation to show the movement of electron pairs. All right, so the first thing that you want to do here is to identify which one contains lone pairs of electrons or double bonds, and that's basically your Lewis base because Lewis bases are electron pair donors. And the ones that are electron deficient or electron poor, those are the Lewis acids. So when you look at this BF3 here, that's a Lewis acid, right? Because it can accept electron pairs to complete its valence shell. So this one is the Lewis acid, and this is the Lewis base because it contains lone pairs of electrons on the oxygen. So now it says use curved arrow notation to show the movement of electron pairs. All right, so I can use purple here. So this lone pair of electrons will form a bond with this boron here. So what you have is this complex right here, where the oxygen bears a partial positive charge and the boron bears a partial negative charge. And the second one here, we have a carbocation. So you see that this carbon here bears a partial positive charge, which indicates that it's electron deficient, electron poor. And this oxygen right here contains so many lone pairs of electrons that it can form a bond with this carbon here. So the movement of electron would be from the base to the acid. So label this the acid and this is the base. And here's another example. Draw the products of each reaction and label the nucleophile and electrophile. All right, so when you look at the starting materials here, we have oxygen that contains lone pairs of electrons, and then we have boron, which is considered electron deficient. So the electron deficient one or electron poor species are known as electrophiles because they want those electrons. Okay, so this is the electrophile, the acid basically. So electrophile. And this one is the nucleophile. So what would the reaction look like? So we have the lone pairs of electrons that will attack the electron deficient boron here. And so now we have a bond that will form between them. So the product looks something like this. So we have oxygen. And now you have a bond between the boron and the oxygen. And then this boron has 3 bromine atoms bonded to it. 1, 2, and 3. All right, and so the oxygen in this case will bear a partial positive charge, and the boron will bear a partial negative charge. And the second one here, we have oxygen containing 2 lone pairs of electrons, and then aluminum that is electron deficient. So again, this is going to be our electrophile. And this one, the nucleophile. So the movement of electrons would be from the nucleophile to the electrophile. Alright, so now we can draw the product here. Aluminum, and then 3 chlorine atoms. And again, this oxygen will bear a positive charge, and then the aluminum a negative charge. All right, what about this second one here? We have a carbocation. So we're going to add carbon, and this carbon has 3 CH3s, methyl groups. And this carbon has a positive charge. It's a carbocation. And so again, lone pair of electrons will attack this carbon, and they will form a covalent bond. So now you have a nitrogen bonded to this carbon, and this carbon has 3 methyl groups. And of course, this carbon will have a neutral charge. And we have a nitrogen that contains 3 ethyl groups, CH3, CH2. And it will bear a positive charge. There it is. So that is the product for this chemical reaction. And the last one here is the reaction between triethylamine and aluminum chloride. And so the, again, lone pair will attack this aluminum, and a covalent bond is formed between nitrogen and aluminum. 1, 2, 3 chlorines. 1, 2, 3 ethyl groups. All right, again, the nitrogen will bear a positive charge, and then the aluminum a negative charge. In some Lewis acid-base reactions, one bond is formed and one bond is broken. And this is usually observed in Lewis acid-base reactions involving pi bonds, double bonds and triple bonds. To draw the products of these reactions, make sure that you keep in mind these 3 steps. Always identify the Lewis acid and base first, and then draw a curved arrow from the electron pair of the base to the electron deficient atom of the acid. And then count the electron pairs and break a bond when needed in order to keep the correct number of valence electrons per atom, or per element. So consider this reaction between cyclohexene, which is acting as a Lewis base, and hydrochloric acid, which is the Lewis acid. We know that this is a Lewis acid because it contains a electron deficient hydrogen or proton, whereas cyclohexene, this is acting as a Lewis base because of the fact that it contains pi bonds, right? So a Lewis base contains either a lone pair of electrons or pi bonds, and pi bonds are present in double bonds and triple bonds. So that would be the first thing that you want to do, is to identify the Lewis acid and base, and then use curved arrows to see where the electrons are going, right? So the electrons here in the pi bond will attack this hydrogen, which is electron deficient within this Lewis acid. So you have a formation of the bond between one of the carbon atoms here with this hydrogen. And then a bond is broken between this hydrogen and chlorine. So what you have is the formation of a new bond, okay? between the carbon and the hydrogen. So again, it doesn't matter whether the bond is between the carbon, this carbon here at the bottom, or the carbon up top. And you'll learn more about this later on in the later chapters. But the point here is that you have one bond that's broken and the other bond is formed. And in this reaction, you have a carbocation that's formed because two of the electrons went to form this bond here in green, the new bond. And then a negative charge is formed because two electrons, the bonding electrons, turn into lone pairs of electrons. So when you look at the net charge of the product, it's neutral, just like the product or the net charge of the starting materials is neutral. And here's practice problem number 35 and also the final example. Label the Lewis acid and base. Use curved arrow notation to show the movement of electron pairs. So the first thing that you want to do here is to basically analyze the starting materials so that we can identify which one is the Lewis acid and which one is the Lewis base. So both oxygen atoms, as you can see, contain lone pairs of electrons, and so they could act as Lewis base. But then when you look at this oxygen right here, it contains protons, right? And so these hydrogens, these protons, bear a partial positive charge. Okay, so that means that these protons are electron deficient because, of course, oxygen is more electronegative than hydrogen. So the bonds between hydrogen and oxygen, these three single bonds here, are polar. They're polar covalent bonds. And so there's a partial negative charge and a partial positive charge, creating that separation charge between the two atoms. So in that case, this H3O plus hydronium ion will act as a Lewis acid, right? Electron pair acceptor. So this will be the Lewis acid. And this one would be the Lewis base. So in terms of movement of electrons, the lone pair of one of the lone pairs here will attack one of these hydrogens. So you can attack this proton, it doesn't matter. They're all equal. And so it will attack this hydrogen right here, for example. And then the bonding pair will turn into a lone pair. And it will go towards the oxygen. Okay, so a bond is formed between this oxygen and this hydrogen. And then a bond is broken between this hydrogen and this oxygen. So what you have is a hydrogen that's bonded to this oxygen. And then a lone pair now on this oxygen.